Good morning, students. I welcome you to the sixth session of mine on electrochemistry. In today's session, we'll be discussing about applications of EMF measurements. By measuring EMF, we can determine many parameters. So there are many applications of EMF measurements, of which in the syllabus we have one of the applications that is mentioned is determination of pH. Second application is potentiometric titrations. So in today's session, we'll be concentrating on the first application as per the syllabus, that is a determination of pH of a solution. So by measuring EMF of a solution, by measuring EMF of a cell, we can calculate pH of a solution, or we can determine pH of a solution. So what is pH? All of us know pH is a measure of hydrogen ion concentration, and it is defined as negative logarithm of hydrogen ion concentration. So pH is a measure of hydrogen ion concentration, and it is defined as negative logarithm of hydrogen ion concentration. So in order to determine pH by measuring EMF of the cell, so the cell that is used to measure pH of a solution should consist of an indicator electrode and a reference electrode. We have learned this. So the cell used to determine pH of a solution should be made up of two electrodes. One is an indicator electrode, the other one is a reference electrode. And the reference electrode that we use is a calomel electrode, saturated calomel electrode. Why we saturated calomel electrode, I have told in the earlier session of mine. Because when we saturated KCl, chloride ion concentration does not change during the storage. Therefore, calomel electrode will have a constant electrode potential. So that's the advantage of using saturated calomel electrode. And the reference electrode has got constant potential. Its potential does not depend upon the concentration of the solution. So it is the indicator electrode which is to be chosen in a right way. So in order to determine pH of a solution, which is nothing but a measure of hydrogen ion concentration, we have to select an indicator electrode whose potential depends upon hydrogen ion concentration, or the electrode which is reversible with respect to H plus ion concentration can be used as an indicator electrode. I repeat, for a cell to be constructed, we need two electrodes. Of the two electrodes, one is the reference electrode and the other is indicator electrode. And the reference electrode under consideration is calomel electrode, because syllabus is using calomel electrode. Therefore, we consider calomel electrode as a reference electrode, that is saturated calomel electrode, and the other one is indicator electrode. So the problem arises with respect to indicator electrode. So when we are measuring pH, which is nothing but measure of hydrogen concentration, so we should select an indicator electrode whose potential depends upon hydrogen ion concentration. So electrode potential which depends on H plus ion concentration. Only such electrode can be used as an indicator electrode to measure pH. So, which are the electrodes whose electrode potential is sensitive to or depends upon hydrogen ion concentration? They are hydrogen electrode, glass electrode, and quinhydrone electrode. So these are the electrodes, quinhydrone. These are the electrodes whose potential depends upon hydrogen ion concentration. So any one of these three electrodes can be used along with the calomel electrode to determine pH. And in the syllabus, we have only two electrodes mentioned, that is measurement of pH using glass electrode and quinhydrone electrode in combination with the calomel electrode. And when it comes to the electrode potential of hydrogen electrode or glass electrode, both of these have same expression, that is we consider reduction of hydrogen ions as the reference reaction, and in case of quinhydrone electrode we have a reduction of quinone to hydroquinone. So we'll discuss one by one. Now let us see. So here reference electrode is a saturated calomel electrode, and indicator electrode is a quinhydrone electrode. So now let us see. This is the combination of the electrodes used to measure EMF of the cell. By measuring EMF of the cell, we will be ultimately calculating pH of the solution. Right. So let us see what is the principle underlying functioning of quinhydrone electrode. So what is this quinhydrone electrode? Quinhydrone electrode is very simple in construction. We use a quinhydrone. It's an organic compound, quinhydrone, which is nothing but 1:1 molar mixture of quinone and hydroquinone. So quinhydrone is an equimolar mixture of quinone and hydroquinone. Quinone is oxidized form of hydroquinone and hydroquinone is the reduced form of quinone. Right. So the reaction that is taking place at quinhydrone electrode, the electrode reaction is that this is the structure of a quinone, or we write like this. So this is a quinone which can be represented by Q, and this is a hydroquinone which can be represented by H2Q. Okay, the difference in the formula is only two hydrogen ions. This is C6H4O2. This is a C6H6O2. So quinone upon reduction gives hydroquinone. Hydroquinone upon oxidation gives a quinone. So this is a reversible redox reaction that is possible. When quinhydrone electrode acts as cathode, forward reaction takes place, and when quinhydrone electrode acts as an anode, backward reaction takes place. So when you look at this reaction, the electrode potential of quinhydrone, so we can represent it as this quinhydrone electrode can be represented like this. So using Nernst equation, E is equal to E electrode is equal to E naught electrode minus of 0.0591 by N log of reduced state by oxidized state. So here E naught plus 0.0591 by 2, because two electrons are involved, log. Since the plus sign is there, in the numerator we have reactants, in the denominator we have products. So in the numerator we have a log of Q into H plus whole square divided by H2Q. So this is the Nernst equation for electrode potential of a quinhydrone electrode. So this is a standard electrode potential of quinhydrone. Now quinhydrone is a mixture of equimolar mixture of quinone and hydroquinone. We learned that quinhydrone is an equimolar mixture of phenone and hydroquinone. So concentration of quinone and concentration of hydroquinone will be equal. So this equation can also be written as, we can separate this log xy can be written as log x plus log y. Plus 0.0591 by 2 log of h plus whole square. So I have split. This is log xy can be written as log x plus log y, and since Q is equal to, that is concentration of quinone, molar concentration. When we enclose a species in square bracket, it means it is a molar concentration. So molar concentration of quinone and hydroquinone being equal to one another, log of Q over H2Q becomes log 1, log 1 is 0. So this equation, this term disappears from the expression. So because of this, quinone concentration of these two species is same, so the ratio becomes 1, log 1 is 0, so this species disappears. And ultimately we have this expression for electrode potential of quinhydrone electrode 0.0591 by 2 log of h plus whole square. So log x to the power y is y log x. So this can be written as into 2 log plus. So this 2 will get cancelled, and ultimately we have 0.0591 log h plus. So the final expression for quinhydrone electrode is this, plus 0.0591 log of h plus. So from this expression, it's quite clear that electrode potential of quinhydrone electrode is dependent on hydrogen ion concentration, because this is constant. Standard electrode potential, I already defined what is standard electrode potential. Concentration of the electrolyte is 1 molar, temperature is 298 Kelvin, pressure is 1 bar. So all these conditions are fixed, therefore electrode potential will be fixed. So this is constant and this is also constant. So electrode potential of quinhydrone depends upon hydrogen ion concentration. Therefore we can use quinhydrone electrode to measure pH of the solution. And E naught, that is standard electrode potential of quinhydrone electrode, is 0.6996 volts plus 0.0591 log H plus. Okay, so we know negative logarithm of hydrogen ion concentration is pH. So we can also write this expression as minus 0.0591 pH. So this is the principle. So quinhydrone electrode can be used to measure pH of the solution, right? So after understanding the principle of working of quinhydrone electrode, now let us see how to measure pH. So quinhydrone electrode is coupled with the calamine. Quinhydrone coupled with SCE, saturated calamine electrode. So quinhydrone electrode is coupled with the saturated calamine electrode. So saturated calamine electrode potential is 0.2422 volts, and that of E naught of quinhydrone is a 0.6996 volts. So when we couple quinhydrone electrode with the saturated calamine electrode, it acts as an cathode. So quinhydrone electrode when coupled with the saturated calamine electrode acts as cathode. Why? Because reduction potential of quinhydrone electrode is more than the reduction potential of saturated calamine electrode. Therefore, we can represent the combination of these two cells as So anode is written first, that is then we have a quinhydrone electrode. So how is quinhydrone electrode constructed? Just by adding a pinch of quinhydrone to the solution whose pH is to be determined, and by dipping a platinum electrode. We have to use an inert metal electrode to make electrical connections, because quinhydrone is a powder. We add a pinch of quinhydrone powder to the solution whose pH is to be measured. Then to connect that quinhydrone with the calomel electrode, we insert an inert metal electrode like platinum or gold. So we use platinum electrode. So platinum electrode is a platinum rod is dipped into solution containing quinhydrone. So this acts as cathode and this acts as anode. And now what will be the ease of this cell? E naught of quinhydrone minus E naught of R. That is, or we can also write E right minus E left. Okay, we are using reduction potentials. So reduction potential of cathode minus reduction potential of anode gives EMF of the cell. So we can write this E cell is equal to E right. Quinhydrone electrode potential, we had written it as 0.6996 minus 0.0591 pH minus E calomel is 0.2422 volts. Right, this is E cell. Okay, so what we do is we construct this cell using the cell using the solution whose pH is to be determined, connect these electrodes to a potentiometer, determine EMF. So knowing EMF, we can calculate the pH. So how do you write this? Bring this side 0.0591 pH is equal to, you take to the other side 0.6996 minus 2.2422 minus E cell. pH is equal to 0.6996 minus 0.2422 minus E cell over 0.0591. So just by measuring EMF of this cell, we can calculate pH. So this is the principle and procedure involved in determining pH of a solution by measuring EMF. So I repeat in short, in order to determine pH of a solution, we need an indicator electrode whose potential is sensitive to hydrogen ion concentration. So the electrodes whose potential is sensitive to hydrogen ion concentration, or the electrodes whose potential depends upon hydrogen ion concentration, are quinhydrone electrode, glass electrode and hydrogen electrode. Other than these electrodes, we cannot use the other electrodes whose potential does not depend upon hydrogen ion concentration. Therefore, and today we have discussed measurement of pH of a solution using quinhydrone electrode. So in order to determine pH, we take quinhydrone electrode and combine with the saturated calomel electrode. And quinhydrone electrode is constructed by adding a pinch of quinhydrone to the solution whose pH is to be determined. Then we dip a platinum electrode, we dip a calomel electrode in the same solution. We need not use salt bridge also. We can place saturated calomel electrode and platinum electrode into the same solution and connect these electrodes to potentiometer, determine EMF of the cell. Now substituting EMF of the cell, we will be calculating pH. So this is how we can determine pH of the solution using quinhydrone electrode. Okay. And quinhydrone electrode has got certain limitations. It cannot be used in the presence of strong oxidizing agents or in the pH above 8. So limitation, though it is very simple in construction, quinhydrone electrode is very simple in construction. We just add a pinch of quinhydrone electrode to the electrolyte and place a platinum rod or platinum electrode, which is inert. So that serves as quinhydrone electrode. So it's very simple in construction, gives reproducible electrode potentials. But at the same time, it has got limitations. It cannot be used for measuring pH more than 8. So it cannot be used in the solutions whose pH is more than 8, that is alkaline. What happens is that the equilibrium between quinone and hydroquinone varies, because quinhydrone is an equimolar mixture, means 1 mole of quinone and 1 mole of hydroquinone are added. It's an equimolar mixture. So when pH is more than 8, this is alkaline. Hydroquinone is acidic in nature, it's a phenolic compound. It's a phenol, right? So this hydroquinone is a phenolic compound, it's an acidic compound. So when pH is more than 8, the equilibrium between quinone and hydroquinone is disturbed. It will, in the solutions above pH 8, the composition of quinhydrone will not be equimolar mixture of phenone and hydroquinone, because hydroquinone gets forms a salt with alkali, therefore equilibrium is disturbed. So we cannot use this quinhydrone electrode to measure pH more than 8. Number 2, it cannot be used in the presence of oxidizing agents also. It cannot be used. Quinhydrone cannot be used in the presence of oxidizing agents. Okay, so because the presence of oxidizing agents will disturb the equilibrium between quinone and hydroquinone, because the function of quinhydrone electrode depends on the equilibrium of quinone and hydroquinone. It's an equimolar mixture. So these are the limitations. Now, second one is determination of pH using the glass electrode. Again, glass electrode is an indicator electrode. So glass electrode can be coupled with calomel electrode, which is the secondary reference electrode, and we can determine pH of the solution. And glass electrode is simple in construction. We take a high conducting glass having low melting point. Okay, I have given in the notes the description of glass electrode. We take a glass of high conductance and low melting point, one end of which is blown into the bulb, and this bulb is filled with 0.1 molar HCl. And to make electrical connections, a platinum wire is dipped and it is sealed. Either we can dip platinum rod or platinum wire, or we can also place silver chloride electrode into 0.1 molar HCl. So this is construction of glass electrode. And whenever this glass electrode is placed into this glass electrode consists of 0.1 molar HCl. And when you place this glass electrode into other solutions containing H plus ions, so there is contact between, okay, there is a bridge between hydrogen ions inside the glass electrode and H plus ions outside the glass electrode. So this results in development of potential at glass electrode. Because of this boundary between H plus ions in the electrode and H plus ions outside the electrode, there arises electrode potential. So that's how potential arises in a glass electrode. And in order to write expression for electrode potential of a glass electrode, we consider this reaction. So the electrode reaction that is taking place is nothing but reduction of H plus ions, which is similar to the reaction occurring at hydrogen electrode. So electrode of this reaction, E glass, can be written as E naught glass plus I use 0.0591, okay, by 1, or you can also take like this, it makes no difference. Either way can do. If I take like this, it becomes 2 log of H plus square divided by pressure of hydrogen gas. So if you keep pressure of hydrogen gas as 1 atmosphere, then if you keep it constant, then what happens is electrode potential of this glass electrode. So sorry, hydrogen, this is not, I'm extremely sorry. Pressure of hydrogen gas does not come into picture because it's a glass electrode. So what happens is that this reaction occurs at the electrode. So we have E glass is equal to E naught glass plus 0.0591 log H plus. So when you look at this expression for electrode potential, again it is clear that electrode potential of glass electrode depends upon hydrogen ion concentration. And E naught G, standard electrode potential of glass, varies with the nature of the glass used. So E naught G will be provided by the manufacturer. So E naught G is constant, right? So you can be determined from the experiment by conducting several experiments with solutions of different H plus ion concentrations. It's a tedious one, right? So we can determine it, or else manufacturers will give us E naught G value, right? So this glass electrode, whose potential is sensitive to H plus ion, is coupled with the calomel electrode. So when it is coupled with the calomel electrode, since the reaction that we have considered is a reduction of H plus ions, electrode reaction, therefore E naught G can also be considered to be less than that of calomel. Therefore we write E cell is equal to E calomel minus E glass. Okay, because the electrode reaction glass electrode is considered similar to the electrode reaction of hydrogen gas electrode. When hydrogen gas electrode is coupled with the calomel electrodes acts as cathode, because E naught of hydrogen gas electrode, that is SHE, is 0. Therefore hydrogen gas electrode acts as anode and calomel acts as cathode. Therefore glass electrode, where the electrode reaction is similar to that of hydrogen electrode, is also assumed to be acting as what? Anode, and calomel electrode acts as cathode, because hydrogen gas electrode and combined with calomel, hydrogen gas electrode acts as anode. Similarly, glass electrode is assumed to be acting as anode, and this expression can be written E glass is E naught glass plus 0.0591 log H plus minus 0.2422, that is electrode potential of a saturated calomel electrode. And this E naught glass can be written as minus 0.0591 pH minus 0.2422. So by measuring EMF of this cell formed or constructed by using a glass electrode and calomel electrode, and dipping both the electrodes, calomel electrode and gas electrode, into the solution whose pH is to be determined, and connecting them to the potentiometer, we can determine EMF of the cell. Knowing EMF of the cell, we can calculate pH. So this is how we can determine pH of a solution by measuring EMF. Only the thing that should be remembered is, in order to determine pH of the solution, we should use an indicator electrode whose potential is sensitive to hydrogen ion concentration. Therefore, the options are hydrogen electrode, twin hydrogen electrode, and glass electrodes. Okay, so let me stop here and we'll continue next class. Thank you. Please keep posting your comments so that I can improve my quality of teaching and quality of videos also. Thank you.